Hi all. Today we discuss the last session of the module 2, the method of Lagrange multipliers. This theorem states that to find the local maximum and minimum values of f subject to some constraint g of x, y, z equal to 0, find the values of x, y, z and lambda that simultaneously satisfies the equation. Gradient f is equal to lambda times gradient g and g of x, y, z equal to 0. For functions of two independent variables, the condition is similar to it, but without the variable z. So that is so analogous to this one. So this gradient f is defined as if f is a function, function of x, y, and z, then gradient f is defined as partial derivative of f with respect to x times I plus partial derivative of f with respect to y times j plus partial derivative of f with respect to z k. So this is the gradient of f. So, and gradient of g can be similarly defined. Gradient of g is obtained by replacing this f by g. So this is the first equation. Gradient of f is equal to lambda times gradient of g and g of x, y, z equal to 0. So that means we need to find out the lambda using these two equations. Okay. Then at those points, at those lambdas, we can get the extreme values, maximum or minimum. So we will explain it in the example 3. We consider f of xy equal to xy, x times y, and we need to find out the maximum or extreme values of this function on this ellipse x square by 8 plus y square by 2 is equal to 1. Okay, so if we can define this f on the whole of xy plane, and we define domain of this is r cross r to R. Even though we define, even though the domain is r cross r, we need to find out the maximum value of this f only on the ellipse. Okay, that's the idea. This is our ellipse. So this function is defined on r cross r, but we need to find out the maximum value of this f on this ellipse. That's the idea here. So in order to do that, in order to find the extreme values, we take this as g of xy. It contains only x and y. So g of xy is this one, x square by 8 plus y square by 2 minus 1. Okay, so we can get the equation g of xy equal to 0, and f of xy is x times y. Okay, so if this is the case, then the gradient of f is defined to be a partial derivative of f with respect to x times I plus partial derivative of f with respect to y times j. Similarly, partial derivative of g with respect to x times I and partial derivative of g with respect to y times j. So this is the gradient in this case. So we need to solve the equations. Del f, gradient f is equal to lambda times gradient g and g of xy equal to 0. Okay, so this is obtained by what is gradient of f? Gradient of f is obtained by, in this case, gradient of f is the derivative of this. Partial derivative of this expression with respect to x first, that will give y times I plus partial derivative of this with respect to y, that is x times j. So this is gradient of f. Then what is gradient of g? Gradient of g is the partial derivative of this expression with respect to x first, that will give 2x by 8, that is x by 4 times I, and partial derivative of this with respect to y, so that will give 2y by 2, that is y times j. So this is gradient of g and this is a gradient of f. So we need to equate it to this equation, yi plus xj equal to lambda times x by 4I plus yj. So this is the first equation. So that is that can be simplified in this manner: yi plus xj equal to lambda by 4 xi plus lambda yj. From this you can get two equations by equating the coefficients of I and j from LHS and RHS. So the first equation will be y is equal to lambda y is equal to lambda by 4 x, and the second equation is x equal to this y lambda. So these are two equations, simultaneous equation obtained from this. Now we can classify this into two cases. Y is equal to 0 is the first case. When y is equal to 0, we can get x is also 0. But this x comma y, that is the point 0, 0, that point does not lie on the ellipse, this x square by 8 plus y square by 2 minus 1 or equal to 1. We need to find out the maximum value of f on this ellipse. But the point satisfying this, in this case, if we choose y equal to 0 and x equal to 0, then those points simultaneously satisfies the system of two equations. Okay, so but the thing is, the point does not belong to that ellipse, so we neglect this one. We are not considering this point because that is not on the ellipse. In the other case, if in the case 2, if you take y not equal to 0, from this you can write, if y is not equal to 0, then you can substitute this equation to here and solve for x. Okay, y not equal to 0, you can get this can be written as from first equation, y not equal to 0 implies from this equation you can get x equal to that 4y by lambda. Though then you can get this 4y by lambda is equal to lambda y. So since this y is non-zero, you can cancel this. Then lambda, that will give lambda square is equal to lambda square is equal to from this you can write by cancelling y, that will be 4. That implies lambda is equal to plus or minus 2, or from this you can write lambda equal to 0. If lambda equal to 0, then you cannot get this lambda square is equal to 4. If lambda equal to 0, from these equations you can get this x. If lambda is equal to 0, you can get y equal to 0 and x equal to 0. So that reduces to the first case. So we are not considering lambda equal to 0 here. That's why we write lambda square is equal to 4 here. Consequently, we can get lambda is equal to plus or minus 2. So we need to find out the value of substitute this value, then we can get we write lambda is equal to plus or minus 2. Substitute this in these equations. Okay, lambda is equal to plus or minus 2, then y is equal to plus or minus 2 by 4 times x, and x equal to plus or minus 2 times y. So from these two you can get an equation y is equal to, or x equal to, from both of these equations you can get x equal to plus or minus 2y. Okay, so this is the value of x. Then we need to solve this equation with g of xy equal to 0. What is g of xy equal to 0? G of xy equal to 0 is this equation, that is x square by 8 plus y square by 2 is equal to 1. Okay, or minus 1 equal to 0. So from we will solve this and this right now. Then substitute x equal to plus or minus 2y in this equation. That will give x square, that is plus or minus 2y whole square divided by 8 plus y by y square by 2 is equal to 1. By solving this you can get 4y square plus 4y square is equal to 8. Okay, by taking the square of this you can get 4y square, 4y square by 8 plus 4 y square by 2, so that is equal to 1. So by taking the LCM you can get this 4y square plus 4y square is equal to 8. Consequently, by taking this is 8y square is equal to 8, that implies y equal to plus or minus 1. Now we can say that the values of y at which this f of xy takes maximum or extreme value is plus or minus 1. If y is equal to plus or minus 1, if we take y is equal to 1 first, then what is the value of x? If y is equal to 1, then from this you can get x equal to plus or minus 2. Similarly, for y is equal to minus 1, we can get still x equal to plus or minus 2. Okay. For both these values, we have x equal to plus or minus 2. Then the points at which this f attains extreme is plus or minus 2, 1, plus or minus 2, minus 1. So these are the points. So we evaluate the functions at these points. Okay. So at the extreme values is x equal to plus or minus 2 and 1. So the extreme values are, if we take, we have 4 points, 2, 1, minus 2, 1, 2, minus 1 and minus 2, minus 1. So these are the 4 points. So if we evaluate f of xy at these points, that will give the values 2 into 1. F of xy is 2 in this case, f of xy is minus 2 in this case, f of xy is again minus 2 in this case, f of xy is 2 in this case. So the extreme values are xy is equal to 2 and xy is equal to minus 2. Okay, so this reduces the complicated steps that we have discussed in the previous problems to find the extreme values of a function with some constraints. Okay, so this is the easiest method. I'll once again explain this. First of all, we consider the function for which we want to find the extreme values and g as the constraint. Okay, then solve del f equal to lambda times del g. This del f and del g are the corresponding gradients along with g of xy equals 0. Okay, find out lambda which satisfies this system, and at those points we evaluate the function and take the maximum and minimum. The geometric idea of this solution is, first of all, we need to find out f of xy equal to xy, the extreme values of this. Okay, when you consider this function, and we need to find out the values at which this f attains maximum. So that means we need to find out f of xy is equal to some c, set of all values like this. Okay, so when you consider this, we call this as the values. If for example xy is equal to 1, xy is equal to minus 2, xy is equal to minus 3, xy is equal to 5, and all, and etc. So these are called the level sets. Okay, level sets of this function. So this will give the hyperbolic rectangular hyperbolas. So that is drawn here. These are those rectangular hyperbolas. And we consider the g or constraint g of xy is equal to x square by 8 plus y square by I think that is y square by 2 is equal to 1. This is the ellipse. So we need to find out the values of this function at the ellipse x square by 8 y square by 2 equal to 1. So we consider all these rectangular hyperbola which intersects with this ellipse, and we need to verify that at the points at which this hyperbola intersect, these rectangular hyperbolas intersect this ellipse orthogonally. Okay, so that is the idea of, at those points we can get this del f is lambda times del g, because this del f and del g give the normal at the points xy. Okay, so if we evaluate del f at x comma y, that will give the normal at x comma y. If we evaluate del g at xy, then that will give the normal at this xy for the curve g. Okay, so we need to find out the points at which this ellipse and this rectangular hyperbola intersect tangentially or orthogonally. This is not orthogonally, tangentially. Okay, if you take this, then the orthogonal will be the same. Okay, or the normal will be same, or the tangent will be the same at those points. Okay, so these are the 4 points. X equal to plus or minus 2 and y is equal to plus or minus 1. These are the only possible values. This is another example. F of xy is equal to this, and x square plus y square is equal to 1. So the geometric meaning is we consider the level sets of this. If we consider our xy plane, this is our xy plane, and level sets of this f of xy, that is 3x plus 4y is equal to 1, 3x plus 4y is equal to c. Generally, if you choose any c, you can get the straight lines with the slope is minus 3. So that is, that straight line is like this. So these are the level sets of the f of xy, and we need to find out the maximum value of this function at this circle. So we consider a circle here. Okay, we need to find out the point at which this level sets or the values of 3x plus 4y touches this or touches the circle tangentially. At this point, we can get, if you consider this is defined using f and the circle is defined using g, then at this point you can get del g is same as lambda times del f. Okay, so this is the idea. So first of all, evaluate del f, gradient of f, and gradient of g. G is taken to be x square plus y square minus 1 equal to 0, and f is 3x plus 4y. So by taking gradient of f and g and equate, then you can get two equations: x equal to this 3 by 2 lambda and y is equal to 2 by lambda. When lambda equal to 0, then this is not defined. So we assume lambda is non-zero. We need to find out x and y for which this holds. Okay, if you choose lambda is not equal to 0, then you can write this x as 3 by 2 lambda and y is equal to 2 by lambda. Then substituting in the equation of the circle, you can get 3 by 2 lambda whole square plus 2 by lambda whole square minus 1 equals 0. From this you can solve for lambda, then lambda will be plus or minus 5 by 2. If lambda is plus or minus 5 by 2, then you can define x and y. So x equal to plus or minus 3 by 5 and y is equal to plus or minus 4 by 5. Okay, so using this x and y, you can find out the values or solve for x and y using this equation. Then you can get x equal to plus or minus 3 by 5 comma 5 by 4. So this is obtained by substituting this values of these x and y in the equation, the equation of the circle. So the values can be written as plus or minus 3 by 5 comma 4 by 5. Now you evaluate the function f of xy at these points. Okay, when you evaluate, we need to find out the maximum value and minimum value of this f at these points. Okay, so that will give one value is 5 and another value is minus 5. So this is the maximum and this is minimum value of f. Okay, so this is how we evaluate the extreme values using Lagrange multiplier method. The last problem is we have a function. We need to find out the extreme values of a function f of xyz equal to x square plus y square plus z square with the two constraints. Okay, the two constraints are xy plus x plus y plus z equal to 1 and x square plus y square is equal to 1. Okay, so here we have two constraints rather than one. Okay, in this case we extend the Lagrange multiplier method with this: del f is equal to lambda times del g1. G1 is corresponds to one constraint plus another parameter mu times del g2. So this g2 is g2 comes from the second constraint. Okay, now we solve using this del f is equal to lambda times del g plus mu times del g2. And along with the two constraints, we have one equation here, and using these two equations, using these three equations, we need to find out the values of this lambda and mu. So by equating this, you can get three equations: 2x equal to 2 lambda x plus mu, and 2y is equal to 2 lambda y plus mu, and 2z equal to mu. Okay, so by solving, you can get 2x equal to 2 lambda x plus 2z, we substitute for this mu. From this 2z, we can get 1 minus lambda times x equal to z, 1 minus lambda y equal to z. Okay, from this you can write x equal to y equal to z by 1 minus lambda. Okay, if z equal to 0, we can get y equal to 0 and x equal to 0. Then in that case, that point is 0, 0, 0, but that doesn't belong to this this equation. Okay, not this one. That doesn't belong to this. Whenever x equal to 0 and y equal to 0, x square plus y square will be 0, but that doesn't satisfy this equation. So we can neglect that number. So assume z not equal to 0. Another possibility is z equal to z equal to 0 with lambda is equal to 1. Okay, that means when you consider these equations, we have the equations 1 minus lambda x equal to z and 1 minus lambda y equal to z. One possibility is z equal to 0 and x equal to 0 and y equal to 0. So this is not possible, that we have discussed just now. And in this case, we have one more possibility with z equal to 1, lambda equal to 1. When lambda equal to 1, you can get z equal to 0 from this equation. You can say that x need not be 0. Okay, x and y are arbitrary. Okay, so that means z equal to 0, lambda equal to 1. This is one possibility. Okay, when lambda not equal to 1, lambda is not equal to 1, you can get that x equal to y is equal to z by 1 minus lambda. So these are two cases we have to discuss. These are the remaining cases anyway. So lambda is 1, lambda is equal to 1, z equal to 0, and x and y are arbitrary. Another case is lambda not equal to 1 and xy takes this form. Okay, so in this case, when z equal to 0, in this case we can write z equal to 0. We write it as z equal to 0 along with lambda equal to 1. We write the equation. We solve these two equations. Okay, z equal to 0. Then in this case, we consider g1 and g2. G1 gives x square plus y square plus y square minus 1 equal to 0, or x square plus y square equal to 1, and this corresponds to g1. And for g2, the constraint g2 is x plus y plus z minus 1 equal to 0. So this is our g2, and by solving this, by putting z equal to 0 in this equation, we can get x square plus y square equal to 1 and x plus y is equal to 1. So this is the these are the simultaneous equations. We will solve these two equations. Then we can get x equal to these 2 points are 1 0 0 and 0 1 0. Since this is z is 0 here, and the value satisfying this condition is 1 0 and 0 1. This is obtained by solving this. These equations are x square plus y square is equal to 1, and put y is equal to 1 minus x from this equation. Then you can get x square plus 1 minus x whole square is equal to 1. Then x square plus, by expanding this, you can get x square minus 2x plus 1 equal to 1. Then you can cancel this one. Then the remaining will be 2x square minus 2x equal to 0. By factor out this 2x, then you can get 2x into x minus 1 equal to 0. Then x equal to 0 and x equal to 1. These are the 2 points. When x equal to 0, then y will be 0. Or the first case is x equal to 0 means y is 1. X equal to 0 means y is equal to 1. Then one point is 0 1 0, and another point is x equal to 1. X equal to 1, you can get y equal to 0. Then the next point will be 1 0 0. That's why we have these 2 points. So we evaluate the function at 0 1 0 and 1 0 0. Then those will give the max extreme values f of x y z as x square plus y square plus z square. This is our f of x y z. Then the possible extreme values will be, in this case, will be only 1. that is 0 square plus 1 square plus 0 square. Similarly 1 square plus 0 square plus 0 square. So that the maximum possible value is 1 here. And in the other case we have x equal to y, that is equal to z by 1 minus lambda. Here lambda is not equal to 1. In this case we solve equations 3 and 4, that is these two equations. The equation corresponds to G1 and G2. So that will give x square plus y square minus 1 equal to 0, because x and y are same. That implies x equal to this one. By adding this to x square is equal to 1, then x will be plus or minus square root of 2 by 2. And by putting x equal to y here, you can get z equal to this point. Clear? So the corresponding points are x equal to this root 2 by 2, and y will be the same, root 2 by 2, then z is equal to this point. And another point is minus root 2 by 2, minus root 2 by 2, 1 plus root 2. Okay, so by substituting the value of x in this equation. So these are the other extreme values. So we evaluate the function at these points. Okay, so these are the extreme values of f. Okay, this is the case when we use the two constraints to find the extreme values. In order to find out the maximum and minimum, we need to verify the values of this. These are, in fact, these values are a point of local maxima. So this completes section 14.8. Now please go through all the portions of second module and let me know if you want any online interactions and all.